Okay, we better get started. It's 13:32, so we want to try and keep to time as much as we can. So session 4, satellite communications and ground segment technologies. What is new? So a lot of this is small aperture terminals and some electronics as well. So anyway, the first presenter is Likit Kristal Smart Antennas for Satcom and 5G, and it's Ahmed Akgiray from ALCAN. Now, just to put you in the picture there, I always thought that ALCAN was a big conglomerate aluminium company of Canada, but it's not. It's you, you're special from Deutschland.
Yes. There you go, seems to work. Okay. Well, hello everyone. First of all, thanks for coming to listen to our presentation. I will try to keep the time. My name is Ahmed Akgiray. I am the Chief Technology Officer of ALCAN Systems. We're a startup in Germany working on liquid crystal-based phased array antennas. And I will sort of try to take this opportunity to introduce what is special about our technology and how we think we can fit in the Satcom and 5G picture. Okay, I mean, this is obviously this is material that you are all very familiar with. So higher data rates, higher frequencies. In the morning session, there's a talk about, low band, mid band, and high band millimeter wave 5G. Satcom, obviously, Ka band is becoming very prominent. And the new non-geostationary satellite constellations and 5G seem to be very promising. So what we are trying to do for these new, obviously the laser doesn't work, for the NGSO constellations and for 5G, we need steerable antennas. And the two options that are currently out in the market is either reflector antennas, motorized, or dishes that turn with motors, or phased array antennas, right? Now, phased array antennas, as you are probably all aware, have been very expensive, so almost exclusively in the military domain, and that's what we are trying to change as ALCAN Systems. What we think is we have a core IP that is very low cost and very low power, and which is something that I will come back to in later slides. That's going to be, we think, critical for 5G as well, low power, which is somewhat, or which has been underappreciated up until now. So beam steering, thin profile, flat panel antennas. That's what we're trying to do. And this is, before introducing the company, I just want to sort of give you a sort of idea of how this might look on cars, airplanes, even homes, as CPE for 5G equipment, or UE as they call them. So who are we? We're a Germany-based startup in Darmstadt, which is very close to Frankfurt. We were founded in 2016. We did our Series A fundraising in 2017. And we have three sort of big investors. One of them is SES. The other one is Merck, the German chemical company, and the other one is BOE. And what we do is, like I said, liquid crystal-based phased arrays. And which part of the phased array is liquid crystal or made of liquid crystal? It's the phase shifters. Right? Liquid crystals are interesting. They consume no power, and obviously with advances in the last 20 years, they've become quite low loss. In fact, if you compare them to a pure semiconductor phase shifter, much less loss to get 360 degrees. Now, what complicates comparison a little bit is semiconductor phase shifters are usually preceded by amplifiers, so you don't really see that loss. But sort of a rule of thumb number that you can take is 7-8 dB loss in semiconductor-based phase shifters, and what we have is, you can think of it as 3 dB. Okay, so half the power. It's still not insignificant, but it's actually quite low. Right. So this is, let's see, this animation we're all familiar with the NGSOs. We're a spin-off from Technical University of Darmstadt. And like I said, in 2017, we did our Series A fundraising, €7.5 million. And we are selected as one of 3 companies for an antenna solution provider for SES's O3b mPOWER constellation. Okay? And we have actually built and demonstrated the world's first liquid crystal-based phased array last year, and we are currently in the process of demonstrating a Ka band. The first one was Ku band, a Ka band prototype that we will be finishing in the next few weeks. In fact, maybe next week. So what do we do? Like I said, it's a phased array. Phased arrays is a proven technology, has been used, has been invented in Germany during the World War II years, and it has been used very widely ever since. Now we combine this with liquid crystals. Right? And what basically, the way we like to think of it is we're trying to take bulky antennas that you see on top of cars, buses, what have you, on even airplanes that look like cathode ray tube televisions, to an LCD panel-like thin display. Right? And liquid crystal has a very unique feature in that it is the only known material with decreasing loss with increasing frequency. Okay, so this makes it a very interesting candidate for example, millimeter wave 5G. And in fact, as a company, we try to sort of focus ourselves in tens of gigahertz range, because that's where the liquid crystal really starts to shine compared to semiconductors. Okay, so like I said, LC loss decreases with increasing frequency. It's been characterized up to almost a terahertz, and it has very high linearity, enables continuous beam steering because you're sort of tuning the liquid crystal, as I will show in just a second, by applying a voltage, but it draws no current. It can have very wide bandwidths, and we have already patented phase shifter topologies with greater than 20% bandwidth. So that makes more than 2 gigahertz at millimeter wave 5G frequency or Ka band Satcom frequency, for example. And we're also, in conjunction with our investor and partner, Merck, we're developing liquid crystals specifically for ALCAN use, for antenna use. And as you may know, Merck is the largest producer of liquid crystals in the world. They supply 60 to 70% of all the LCs that you find in your displays. So here's our animation. So what you are seeing here, let's see if I can, no I don't. Okay, I'll try to sort of point to it. The laser doesn't work. So what you are seeing here is a cross-section of an example, what we call microstrip line in RF microwave engineering. The yellow bottom electrode is ground, and the top yellow electrode is signal. And right now, as the picture shows, what you have in between is the liquid crystal molecules. Okay, no voltage applied. There's an alignment layer, so they stay in a certain alignment with respect to glass. Glass is the white boxes or the rectangles that you see. Now, if you start, let's see, try again. There you go. So there is the electromagnetic field, RF field, with respect to the liquid crystal molecule, the orientation. Right now they're at 90 degrees, right? And this presents a certain epsilon, what we call perpendicular dielectric constant. And once you start applying a voltage, the liquid crystal molecule physically starts to rotate. Right? And the more voltage you apply, the more it rotates. And now the molecules and the fields are aligned, and this presents a different dielectric constant to the RF field. And this is how we tune the phase, because effectively we're changing the length of this transmission line by changing the dielectric constant of the medium. So why do we say we think we can be the lowest cost and lowest power? Well, the power is the easy one, because the phase shifters consume no power. Right? I should not go over time, so I'll try to speed up a little bit. Now, cost-wise, these phase shifters that we have been designing are produced in LC panel factory lines, right? With little to no modification. Okay, so as you have witnessed the prices of LC displays come down, order of magnitude perhaps, from when they first started. So we're taking advantage of that economies of scale, if you will. Right? So we think we can be up to 100 times cheaper compared to a semiconductor-based solution, up to 30 times lower power compared to a semiconductor-based solution. Obviously, these comparisons, depends on scenario by scenario, but at least an order of magnitude, maybe up to 20 times in terms of power. So I'll try to speed up. Our first product, which is due to come out next year, it's going to be an all-passive, because the phase shifter is low loss, it's going to be an all-passive antenna, steerable in 2D plus minus 60 degrees. We have other designs plus minus 45 and so on. And it's a modular design, so we can build terminals, 3 dB over Kelvin, 9 dB over Kelvin, 15, 12. 15 is probably the biggest that makes sense to go. We have separate apertures, receive and transmit, and we are also working in parallel for integration of low noise amplifiers and power amplifiers with the liquid crystal layer, because for some applications, especially KU band, that's usually necessary, otherwise the antenna can be really large. So this is kind of a not-to-scale stack-up of our antenna, if you will. The LC phase shifters, the glass or the panel, as we refer to it, is in the middle. You have some sort of feed network below it, and radiating element, and so cover or radome on top. This is a picture of our first, or the world's first LC-based phased array, demonstrated last year, and as I said, we are currently in the process of demonstrating a Ka band LC-based phased array, all passive, and in the next couple of weeks. When I say next couple of weeks, 2 to 3 weeks, all the parts are in. It's just a matter of assembly and testing at this point. And in terms of target markets, we think we can be in a lot of different places. When the company started, we were looking at RV market, and then we switched to fixed terminals, kind of enterprise antennas, and that's what we're building for SCS O3BM power. But we really think because of this power and cost advantage, there's a role for ALCAN or LC-based phased arrays in 5G as well, and we're in discussions with all the big manufacturers in the 5G domain as well. So I'm sorry?
2 minutes?
Yes, I'm just wrapping up. I think this is next to last slide, and we can take questions. Ultimately, what is our ultimate goal is the connected car. We want to be, and we actually have sort of research projects going on for sort of antennas embedded in glass in sort of transparent kind of thing, using LC again, and things like that. So I think with that, I will stop. If you have any questions, I'd be happy to try to answer.
Yeah, we have a panel discussion, so
okay.
We'll give you a rest. You have a rest now, okay. And you go and sit down, and then you come up here on the chairs, okay. And that's when all the questions come along. Okay. Right. Thank you very much indeed. Excellent. Something new. Something new. Okay.